want to show you how you can analyze beam spanning more than 10 meters long. You can see I have a beam here, beam L, which is spanning 11 meters. So this is another Prokon gig. Because analyzing this beam can be quite tricky and quite difficult, and you're not sure because you need to provide a safe design, and at the same time you need to provide an economical design. You need to make sure that the depth is okay in terms of short-term and long-term deflection. You need to make sure that the reinforcement is enough. So this beam is, there is no flap here. If I can show you the 3D render. So okay, so there is no, I think this one is just a roof, so this one does not have a slab, and thank God, because I think this span is too long, and you can see we have a load here, we have this load here, so we need to consider this dead load here on top of this critical long spanning beam. So I will open Prokon, go straight to Prokon, and I will open Prokon. So I think engineers plan continuously, because even me, until I faced this challenge, I didn't know how I can or I should handle such a challenge. But now I do, and I want to share with you, my viewers. And I really thank you for supporting and subscribing to my channel. And I'm 400 subscribers right now, so I really appreciate. So let's continue. So I've opened Prokon, and then go to continuous beam. This is the first option. First, go to concrete, then continuous beam. Because I think doing this manually is much better, and Prokon usually is like manual, because you're the ones who is going to determine the loads and the spans and everything. So you are not just going to model the wall and then the software analyze for you. You can just calculate the load, and then you know we will get to know which should be the maximum load for this wall here, so that we know that how limited we are, and what we cannot exceed what amount of load on this, because this span is too low. So I'm going to change these ones. I need to use plus 25. I need to use for 60, and I will also use for 60 over here. Then I can just change the covers to 25, then again 25. My density of concrete is okay, and just 24.5. And then you can go to sections. So if you check this plan, these two columns. So these columns are 40 meters apart, and each column is 300 millimeters in depth, in diameter. So 150 millimeter radius. So this one, so the distance between this center and this center is 340. So this here is about 40. So you can see it's 340. So I'm going to just put those values here. So let me first put the sections. I have how many sections? 3 sections. 1, 3. So I will just use the 50. I'll just start with 50 by 600 because that span is so critical. It's too long, like almost 12 uh, meters. So it's not advisable to have such span, but it's there. So you have to analyze. Just put my span 1, span 2, left span 3. My section length is 0.34. That is my first span. My second span is 11.32, and the other span is 0.34. So I will put my supports. Support number 1, number 2, number 3, the upper support, and number 4. So if you put C, it means it's a cantilever. If you put F, it means it's fixed maybe in another beam. Okay, but it's a column, so you just need to put the depth of the section of the column, that is diameter and depth. So that is the H and the B. So I'm going to put my depth just 300, again 300, 300, 300. Then my height is 5.8. 5.8. Okay, I don't have columns above. I'll go straight to load. Okay, I have load case 1, dead load, span 1, span 2, span 3. I don't think I have live load there, so I can just put the dead load. Maybe if it's live load, it's very insignificant, maybe very small. So just put the dead load, and that the dead load should be the self weight of that beam plus the weight of these wall. So how do I calculate the self weight of that beam? Let me open one to do the calculations. Okay, so I'll open a new one. Now, just so self weight. I should put that will be the depth, that is 0.6 multiplied by the width, that is 0.25 multiplied by the density of concrete, which is 25 kilonewtons per meter cubic. So this one is self weight. So to do the maths, hope you have the calculator nearby to do this together. So that will be 0.6 multiplied by 0.25 multiplied by 25. So I get the self weight to be 3.7. Okay. That is the self weight of that beam plus the weight of this load here. It's a wall, but you can see the way the shape. Based on the shape, I think this wall is about how many meters long? Let's use the architecture. This is the architecture. Oops, so if you use the architecture, I can still know the height. I think it's somewhere between here and maybe it's on the other side. So if I can check it, you can see it is about 1.5 plus 4.5, that is 6. So we will use half of it. Half of it will be, because it is, the shape is like this, it's a triangle. So we will use height to be half of it. So the height, so find the weight of this. Maybe you are using 20, you're using bricks which are 20, the masonry which is has a unit weight of 20 kilometers per meter cube, multiplied by the height, that is 3, multiplied by the depth of that brick, maybe 0.2. So we find this load here. So that one will be again multiplied by 2, because this one looks like that. That one will be 20 multiplied by 3 multiplied by 0.2. So the height is how many meters? 20 multiplied by 3 multiplied by 0.2. So does that give me 12? So the depth is 0.2. Let me see. So let's do this shape again. Let's do the architecture. But I really doubt this one cannot be brick. Even if it is brick, I don't think so. The material that we going to use here is not stones. So maybe I can use a envelope of maybe, let's say 12. That's how that's what we find here. It goes to 12. Let's try 12. So it has a load of 12 on, that is 12 kilograms per meter. That is that is distributed. So let's view. Okay, no section. So let me go back to section and do beam number 1. So how many beams do I have? I have 3 beams. I have, check this architecture. I check my plan here. I have this beam, this, and beam. So we have 3. I don't know where the area is coming from. I have 3 spans. Just move 1, 1, 1. So that area is gone. So you can see the deflection. So basically, we need to know if these are fast. So the elastic deflection is 6.4 millimeters, and the long-term deflection is 41.99 millimeters. That is 42 millimeters. So we know that for from the BS curve, ultimate deflection equals to L over 500. That one will be 11.32 over 500. do that, it would be about 22 point something. That let's do this together. 22 divided by 5. It's 22.64, right? So that is millimeters. And you can see our deflection here is 42. So this one has failed in deflection. So let me run this one. Let me erase. So we see that the ultimate deflection, the deflection is 42. That is the maximum long-term deflection. Deflection, which is greater than 22.6 millimeters. So therefore, depth of D is equal to 600 millimeters, not okay. So, and remember this one is also based on the reinforcement. So let us try to increase the reinforcement. Let's see the moments. The moment is also exceeding. So we know we are increasing the moments. The maximum shear capacity is exceeded. So it has also failed the maximum shear capacity. So that's why we know that if I go here, maybe I should change this load. Let's check. Let's see the maximum load we can use. So I will reduce it to 10. So let's read. So let's reduce it further to maybe 8. But I'm sure those things are not blocks. They are maybe just hollow bricks, so not that way. So if I go to view, yeah, you can see now we have not exceeded the maximum. So the shear is now passing. So the steel, these are the curves output, crank. So if we go to reinforcement, I need to use, because from experience engineer they advise you to use 20, at least 20. I just need to use 20 maximum and minimum, then 20, then 20. Startups are okay, then let me just wait. Okay, let's now view our deflection. Now our deflection has reduced to 19 by 0.59. Okay, but now check this out. The load here, the load that I have used here is 8. Maybe I need to use a load of 10. So the load also determines. Let's see if, let's view. Now we can see let me see the shear. The shear has been exceeded. So let's increase the depth. We'll increase the depth to 650. 650. Again 650. Okay, so let's view response. Let's view maximum deflection is okay. Now the shear is not exceeded because I think maximum shear is not exceeded. So it also depends on the load that you are going to assign. Maybe you need a load of 11, 11, based on your calculations that you have done manually, based on the material that they are going to load here. Based on the material that they are going to load here, you know the load that is required. So from my calculation, the load was 12 because that shape looks like this. That shape looks like so let me go back. Yes, that shape looks like this. So the height cannot be the average height will be half about there. So it will be at maybe at 3. So 3 multiplied by maybe 18 multiplied by the thickness. Maybe the thickness is 200 or something. So just 0.2. To do the calculations, it will be 3. That is the height of the wall multiplied by the unit weight of masonry. That is 18 multiplied by 0.2. We find it is equals to 10.8. That is what we are going to load here. If we load 10.8, so let's view moments. Maximum shear moment has been exceeded. So no, I'm sure that they are not blocked, and even if they are blocked, they may be having hollows because you can see. So I think for me, our 10 will be okay. If I use 10 and it is passing, then that one will be okay. Going to input load. If 10 is passing, then the structure is very okay because I'm sure those are not are just bricks with with shapes maybe hollow. So they can't be just as heavy as just normal masonry, which is completely a block. So if this one is passing, then we are very okay. So let's do deflection is okay. Our maximum deflection is 19, and now we calculated our ultimate deflection is 22. So 19 point, you see this from here, 0.4, 0.5 is less than 22.6. Therefore, B is equals 600 millimeters. That is 650 millimeters is okay. Now, because if we go to reinforcing, main reinforcement, because this beam might experience some erosion because of the depth, I may just add a middle one. So I'll click, I may change this one to 16 and maybe change the length, the full length, that is 12.25 or 11. Just I can just change it to 11.82. So I will just click here, select there, and then paste. So the length is spanning all the way. Okay. So up to maybe I can just say 12. Just 12 is okay. Yeah. So now if you view, We can see that one does not help in terms of reflection, but in terms of torsion. So now we can go to shear reinforcement. I will based on ASP maximum. Do the calculation, realize given the spacing of 1 inch. So we go to calculation, beside the output, on output, if you need to include everything, including input sketches, output file, tracks. I will not include the posing table, posing diagrams, and posing graphs. Okay, so if you check, we see now you have included. I will include inputs, outputs. So this one I think is bending moments and reinforcements. So you need to include these, but for me, I will not include all these because I keep making my paper too long. Okay? Making my calculation too long. So I will not include that. And just go here and exclude those. Actually, exclude those. So these ones are what? Very and moment. So I want to exclude those imposing tables and then posting diagrams. Wow. I exclude this. Yeah. So I just need to print this and maybe add my calculation for checking deflection here. So I must include the deflection, that is deflection value, so that I will show I check the deflection and it will reflect. So guys, thank you, and I have reached 400 subscribers. I really appreciate. So please keep on watching my videos. I will keep on updating you and putting work that you really like, not just because my aim is not just to get or something. I just need to solve problems. If I solve problems, and that is what to make me even more happy. So, friends, see you in another